Presentation at this international conference. I'm just sorry that I can't actually attend in person. And I'd like to take the opportunity to thank Pei for the invitation to make this presentation. This slide just shows some of my disclosures. So what I would like to do in the next 25 or so minutes is to tell you three short stories based upon our experience of targeting solid tumours using CAR T-cell immunotherapy, starting out with a technology which by now is over 20 years old, in fact, so-called second-generation CAR technology, and then moving forward into some more recent CAR architectures, which we have been working with a view to improving efficacy against solid tumours. So to start out, let me tell you about a clinical trial involving a second-generation CAR, which has been running at Guy's Hospital in London since 2015. This involves a product which we refer to as T4 immunotherapy, and this is a CD28 containing second-generation CAR. The targeting moiety, which is shown by the red blob on the exterior of the receptor, is not an antibody fragment, but instead is a chimeric polypeptide known as T1E. This is a promiscuous ERB-B ligand. It can target 8 of 9 ERB-B homo or heterodimers. And so in designing this so-called Ti-28 zeta CAR, our intention was to achieve broad targeting specificity right across the ERB-B network, given the frequency with which this network is dysregulated in common adult solid tumors. Now, we're using a retroviral vector to deliver this CAR to the T cells, and we're very conscious of the fact that in attempting to transduce T cells from patients with advanced malignancy, efficiency of gene transfer can sometimes be challenging. And to address that issue, we co-express the CAR with a chimeric cytokine receptor known as 4-alpha-beta. This is a fusion of the IL-4 receptor on the outside to the shared beta chain used by the receptors for interleukin-2 and interleukin-15. Interleukin-4 itself is a very poor growth factor for T cells, but if you add IL-4 to T cells which express this 4-alpha-beta chimeric cytokine receptor, it causes that receptor to pair up with the common gamma chain in those T cells, driving a selective growth signal only to the retrovirus transduced T cells. So it's a manufacturing ploy that we use to ensure high transduction efficiency of these cells. Now, the elephant in the room in this whole story is safety. How can you ever conceive of targeting the entire ERB-B network with a CAR T cell and hope not to see significant toxicity? And with this in mind, we selected head and neck cancer for this clinical trial, given the fact that locally advanced or locally recurrent tumor formation is the main clinical problem that these patients encounter. Here you can see an example of a locally advanced tumor, and we viewed this as a clinical disease model with which to test the safety of intratumorally delivered CAR T cells. And you can see a number of other reasons that we chose this disease summarized on this slide. The target is essentially ubiquitously present in these tumors, and there's still a very significant unmet clinical need for better treatments for this tumor type. Now, if patients have untreatable head and neck cancer, the survival curve shown on the right of this slide illustrates their prospects. And as you can see, they have a dire prognosis with a 100% mortality due to tumor progression within 30 weeks. And those deaths begin to start literally from day one of patients being assigned this prognosis. This was a really important ethical justification that we made to our regulatory authority, the MHRA here in the UK, in order to secure permission to undertake this clinical trial. So this is a phase 1 dose escalation study in which we have a 3+3 design, meaning that we treat 3 patients at the first dose level, and if we do not encounter a dose-limiting toxicity, we move on to cohort 2, treat another 3 patients, and so on through 5 dose levels summarized on the bottom left of this slide. So the first patient cohort were treated with 10 million CAR-T injected directly into a target lesion, whereas the final and fifth cohort receive a dose of 1 billion CAR-T cells. And as you can see, the CAR-T cells are formulated in a volume of between 1 and 4 milliliters as a fresh product, which is then injected directly into the tumor. The inclusion and exclusion criteria are pretty standard for a phase 1 clinical trial of a new cancer medicine, and as you can see, they are summarized on the right of this slide. This is a rather busy slide, but it summarizes the patients who were enrolled during the dose escalation phase of this trial. As I mentioned, there are 5 dose levels with 3 patients per cohort, so all going well, you would expect to see 15 patients on this table, but in fact there are 17. And the reason for that is that patient number 5 died of his disease during the 2-week period that we were manufacturing his CAR-T cell product. That gives you, I think, a sense of the kind of patients that we are enrolling in this trial and how fragile these patients can be. Patient number 12 was also not treated because he had a vascular invasive tumor at the time of screening, and therefore he failed because we could not safely inject CAR-T into that lesion. There are a number of other take-home points from this slide. Firstly, these patients do not receive any conditioning therapy. No lymphodepleting chemotherapy or other conditioning is administered. The patients simply receive the target dose of CAR-T cells injected into 1 or more tumor lesions. The second point to mention relates to the prior treatment history of these patients. These are very heavily pre-treated patients with up to 8 lines of prior therapy. And one final point, if you look at the age column over on the left of the slide, you see we've got quite a range, but actually 2 of the patients were over the age of 80 and yet were safely treated with intratumoral T4 immunotherapy. Our manufacturing process is quite distinct compared to that used with, let's say, with the licensed CAR-T products. We do not start with an apheresis procedure, but instead start with a blood draw. Typically, patients donate 130 milliliters of blood, of which 120 mils come into our GMP facility, and the remaining 10 mils undergo sterility testing. However, in one case, we only started out with 40 milliliters of blood, and yet these small volumes of blood are sufficient to manufacture between 2 and 7.5 billion CAR-T cells in between 10 and 14 days. In fact, using this method, we did not have any batch failures. All of the manufacturing runs were successful without the need for a second attempt in the case of any patient. You can see the expansion of the T cells on the left of this slide, and you can see the transduction efficiency measured at the midpoint and the end of the 2-week manufacturing process, illustrated graphically on the right. Notice how the percent CAR-positive cells increases when you compare midpoint and endpoint, reflecting the selective advantage that interleukin-4 confers upon the retrovirus transduced T cells. The products that we generate are quite variable, although there is a tendency for these to be CD4 rich, and that may well be an attribute of the IL-4 based expansion process. These products are mainly enriched in central and effector memory T cell subsets. Intratumoral T4 immunotherapy has proven to be very safe. We have not seen any dose-limiting toxicities, no cytokine release syndrome over and above pyrexia, and no evidence of neurotoxicity in any of these patients. The typical reaction that we see in these patients is a local inflammatory response within the target lesion, which becomes painful, inflamed, swollen, and the patients typically develop fever, which is generally gone within 24 hours. There was no evidence of on-target off-tumor toxicity in this trial, and the reason for that is summarized on the left of this slide. In other words, when you look by qPCR in the peripheral blood, you cannot find these CAR-T cells at meaningful levels in any patient at any time post-treatment. I mentioned that the patients develop fever after intratumoral CAR T, and that pyrexia, its duration, does seem to be dose dependent in the sense that 2 of the patients in cohort 5 had pyrexia which persisted beyond 24 hours. And as you can see, that was accompanied by increased levels of cytokines in the peripheral blood of the cohort 5 patients. Those are indicated by the green lines, which represent separate plots for each of the 3 patients in the highest dose cohort. So I've mentioned already about the safety of T4 immunotherapy. From an efficacy perspective, T4 immunotherapy is not CD19 CAR T. I wish it were, but nonetheless, there are some pointers to indicate that this product does have some anti-tumor activity in these patients. And I make that statement for a number of reasons. Firstly, in the terminal stage of the disease, these tumors tend to grow extremely rapidly. They often more than double in size in 6 weeks. However, of the 15 patients treated with T4 immunotherapy, 9 of these patients achieved stable disease, summarized by SD on the table, as measured by RECIST criteria. Another reason I think that we're seeing an efficacy signal in this study relates to the survival of these patients, which is summarized on the left of this slide. As I mentioned earlier, without treatment, we expect all of these patients to die within 30 weeks, in other words, 210 days, whereas you can see that the survival curve, which is plotted in days on the left of this slide, shows that many of these patients survive well beyond that time point. And indeed, you will notice that one of the patients was a long-term survivor. He achieved stable disease with T4 immunotherapy and subsequently was treated with anti-PD-1 pembrolizumab and the oncolytic virus T-VEC, prompting a complete response of a tumor which was literally the size of my fist. He remained in CR for over 3 years, in fact, before relapsing. The plot on the right of this slide shows that the stable disease achieved in these patients was not dose-dependent. We also tried to interrogate what attributes of the CAR T-cell product might be predictive of a better or indeed a worse outcome for patients. And what we found comparing the stable disease and progressive disease cohorts was that better outcome tended to be linked to a higher CD4 to CD8 ratio, lower expression of certain exhaustion markers such as TIM3 and CD39, and higher expression of the GLUT1 glucose transporter on CD4 T cells in the product. There was also a weak association with polyfunctionality and increased cytokine production in terms of better outcome for the patients. This is my final slide on the clinical trial, and it shows something that we did in only one of the patients, where we took an aliquot of the CAR T-cell product, labeled it up with radioactive indium, and injected this radio tracer into the target lesion. You can see here in the day 1 SPECT CT scan that all of the area that I'm encircling with my cursor, this is all tumor. And you can see that the radio tracer is injected on the top of the target lesion, a little bit like a cherry on top of a cake. If you repeat the scan at 24 and at 48 hours, you can see that the signal from the radio tracer does not move at all. The good aspect, I guess, of this is the fact that we're not seeing systemic absorption of these CAR T cells, as I've discussed earlier. However, what this also shows, which is slightly less positive, is the fact that these T cells are not capable of infiltrating into the target lesion. They stay where you put them. Okay, so that was a clinical trial involving a second-generation CAR T-cell in a solid tumor setting. And whilst there are some grounds for encouragement, it seems clear to me that we need better CARs if we are going to make a real impact against solid tumors. Now, the breakthrough of CAR T against blood cancers came from second-generation CARs in which co-stimulation is either provided by CD28 or 4-1BB. People have attempted to integrate both of these forms of co-stimulation using third-generation CARs, but clinical results in adults have been disappointing. And when we investigated this, we found that using this linear architecture, the downstream of those two co-stimulatory domains does not function properly in that non-physiological location. To fix this problem, we designed an architecture which you can see on the right of this slide called a P-CAR, or a parallel CAR. And what a parallel CAR consists of is the co-expression of a second-generation CAR, for example, containing CD28, alongside a second receptor, a chimeric co-stimulatory receptor, which contains a different form of co-stim domain, such as 4-1BB, for example. With this parallel CAR architecture, this means that both of the co-stimulatory domains are located in their natural position next to the plasma membrane. To test this architecture, we started out with a model system in which we have a tumor monolayer which expresses a target antigen, the colony-stimulating factor 1 receptor. We selected this model because there are two natural ligands for the CSF1 receptor, namely CSF1 itself and interleukin-34. And we could use those two ligands as targeting moieties to build a whole panel of CARs, second generation, third generation, and also parallel CARs. To test these various CAR T cells, we carried out tumor restimulation experiments on tumor monolayers which express the CSF1 receptor. And what we found was that when we restimulate these T cells, the T cells maintain the ability to proliferate on the tumor monolayer through 4, 5, 6 cycles before the onset of exhaustion. However, the parallel CAR T cells shown on the bottom left of this slide could be re-stimulated through many more cycles on average before they would become exhausted. When we then moved this in vivo, we made CD19 targeted parallel CARs, making comparison with matched second generation CARs, which contain the same binder, or an analog of the KITE approved product, which is a CD28 containing second generation CAR. The survival curves that you can see on this slide are of animals with an established BALL NOM6 leukemic burden, and we are treating the animals with a suboptimal dose of CAR T, 500,000 T cells, because we're not trying to cure the mice, but we're trying to unpick differences between the second generation CAR and the parallel CAR. And as you can see in 3 separate examples using different parallel CARs, we see superiority compared to the traditional second generation architecture. Here's another example. This is a head and neck solid tumor xenograft model. The animals have an established tumor burden, and we treat with either a second generation CAR, which is the Ti-28 zeta CAR that I told you about at the beginning of the presentation, or a matched parallel CAR. As you can see initially, the two products work very well, and the tumor is completely eradicated in the mice in all cases. On day 63, what we then did was a tumor rechallenge, and that's shown on the right. So you can see that there is an upward inflection of bioluminescence, confirming that the tumor has indeed been injected into the mice, after which the tumor burden goes back down to baseline in the PCAR group. However, the second generation group, shown by the purple line, establishes a smoldering tumor burden, confirming that the rechallenge has not been fully rejected in these mice. And finally, let me move to a second architecture which we are working intensively on at Lucid Bio at the moment, which we refer to as an adapter CAR. If you think about it, most of the CARs that have been described so far have a linear structure in which a targeting moiety, spacer, transmembrane domain, and signaling domain or domains are fused together in series. However, many natural immune receptors don't have that type of structure, but instead have an adapter structure whereby the ligand binding domain and the signaling apparatus are physically separate from each other, different polypeptides. An example of an adapter receptor is the NKG2D receptor, which naturally associates with an adapter molecule called DAP10. And we have taken that natural structure as a starting point to build CARs, which retain this adapter configuration. So these CARs are targeted using NKG2D against 8 so-called NKG2D ligands. These ligands are widely expressed in both solid and blood cancers, so we think this is a potentially attractive opportunity to target broadly against cancers using NKG2D itself and this adapter architecture to give us this more natural structure. The CAR that we started out with is referred to as LU002, and you can see a kind of cartoon illustration of its structure on the right of this slide. Now, one of the attractions of NKG2D ligands as a target in solid tumours is the fact that these ligands are not just expressed on tumour cells, but they are also expressed on stromal cells in the tumour microenvironment. And we have simulated that using a 2D model, which you can see on this slide, in which you have islands of tumour cells, and I'm drawing my cursor around one island of tumour cells at the moment. These islands of tumour cells are interspersed with mesenchymal stromal cells. And the stromal cells separate the tumour islands and almost protect them from the outside world. In pancreatic cancer, only about 10% of the mass of the tumour is actually malignant cells, and the rest is stroma, such as fibroblasts, stellate cells, and of course immunosuppressive leukocytes as well. Now, these stromal cells produce chemokines which naturally attract T cells to that location. And what these T cells are doing when they're sitting in the stroma, what they are not doing, I should say, is attacking the tumour. But this is not a defense against NKG2D targeted CAR T, because the stromal cells are also stressed and consequently upregulate NKG2D ligands. So let me show you what happens if you add LU002 T cells onto this system. You will notice that the first place they go for is the stroma. And so now you can see that the T cells have gone straight for the stroma and they are destroying it as I speak. The tumor cell islands appear to coalesce almost in an attempt to evade the T cells. But as you can see, the T cells are now directing their attention to the tumor cell islands, which are also dispatched. You can also do this in a tumor spheroid system where you mix together tumor cells and mesenchymal stromal cells, and they form these tight balls of cells, which we refer to as tumor spheroids. If you add CAR T cells to the spheroids, they have to break into that tight ball of cells in order to recognize the tumor and the stromal cells contained therein. If you look at what happens when you add untransduced T cells over on the left of this slide, you can see that the spheroids remain completely intact because, of course, the untransduced T cells do not attack them. And you can still see the spheroids with the naked eye. And if you deaggregate the cells and put them through a flow cytometer, you can see that the tumor and stromal cells fall in a separate gate to the T cells. If you now move to the right of the slide and see what happens with the adapter CAR, LU002, you can see that nothing remains visible to the naked eye. And when you deaggregate what remains in the tube, you can see that really all you can see are activated T cells, some of which are beginning to spill into the tumor plus stroma gate, because of course activated T cells become much larger and they change their scatter profile. With a linear NKG2D CAR, what you see is an intermediate profile, whereby the spheroids remain visible to the naked eye, and the tumor and stromal content has clearly been reduced, but there is still a lot of residual tumor remaining at the end of the experiment. One of the problems with CAR T cells is that they do not form natural immune synapses in contrast to TCRs. However, LU002 adapter CAR T cells form a highly organized bullseye type immune synapse, which you can see on the bottom right of this slide. This is turf microscopy of LU002 T cells placed on top of a lipid bilayer, which expresses an NKG2D ligand called MICA. These LU002 CAR T cells have very significant anti-tumor activity in animal xenograft models. On the left, we have a pancreatic tumor xenograft model, which, as you can see, is completely resistant to traditional second-generation CAR T cells, indicated by the blue line. But the adapter CAR, LU002, eradicates the tumor in all of the animals. And if you inject tumor once again on day 88 and thereby perform a tumor re-challenge, this is also rejected. And you can also see a similar story in the mesothelioma xenograft on the right of this slide. Here's a third example. This is a mesothelioma PDX, which is very slow growing. It's been established in the mice for over 100 days, after which we treat with intravenously administered LU002 CAR T cells, shown by the orange line. Note the rejection of the tumor in 6 out of 7 of these mice, whereas a linear NKG2D CAR, shown by the blue line, has no efficacy in this model. So the next stage in the story is the move from LU002, an adapter CAR, targeting NKG2D ligands, to an armoured version of this car, which we call Lu011. The only addition in Lu011 is a homing receptor, which exploits small molecules released by solid tumours in order to direct their trafficking towards the tumour. So I'm going to run three movies in a moment, which show you a tumour spheroid growing in a high density of matrigel, to which we add CAR T cells to the outside of the matrigel. So in other words, the CAR T cells have to burrow their way through the matrigel in order to find and eradicate the tumour spheroid. So let me run the movies simultaneously, and I would ask you first to concentrate on the right of the slide, the Lu011 condition, where already you can see that the growth of the spheroid is lagging behind the other two. By day 2, which is coming up in just a moment, you will notice that the spheroid becomes completely transparent and stops evolving, and there it goes just now. This is because the spheroid has been completely destroyed, and what you see is a cavity remaining in the matrigel. If you now concentrate on the movie in the middle, the Lu002 movie, you will see that it takes up to 4 days before a similar transition happens. So now you can see that that spheroid is also transparent, and there is a dark halo around the spheroid. Those are T cells, which have taken a longer time to get into the site of the tumour than is the case with Lu011. If you now look at the untransduced T cell condition on the left of the slide, you can see the movie has finished, but that spheroid has clearly infiltrated into the matrigel in a very tumor-like fashion. In order to compare Lu002 and Lu011 in vivo, we set up a subcutaneous tumor model. This is a pancreatic tumor injected subcutaneously in NSG mice, and we then treat the animals with intravenous CAR T cells. The control in this experiment is labeled as NKG2D. What we've done here is simply to overexpress NKG2D in the T cells. That's indicated by the purple line, and as you can see, those T cells have no therapeutic activity whatever in this model. If you express a linear CAR in these T cells where you fuse NKG2D to CD3 zeta, that is labeled on this slide as NZ. And as you can see, the NZ linear CAR T cells control the tumor until day 50, after which the tumor grows out. That's indicated by the pink line. If you move to the adapter CAR, Lu002, that's indicated by the green line. You have tumor control until day 100, followed by tumor outgrowth. The armored version, Lu011, controls the tumor in all of the animals, giving a significant survival advantage. How do we know this Lu011 is in fact homing to the tumor? Well, that's illustrated on this slide here, where we have a tumor growing in the peritoneal cavity, and we are imaging the CAR T cells. And if you look at the 72-hour time point following intravenous administration of the T cells, you can see how many of them have gone to the tumor, by contrast with the adapter CAR alone, Lu002, where the signal is much lower. If you only remember one slide from this presentation, this is the one I would ask you to recall. This is a pooled survival analysis of mice treated in 10 separate solid tumor xenograft experiments, comparing the linear CAR NZ, the adapter CAR Lu002, and the armored adapter CAR Lu011. Note how the linear CAR gives a survival advantage compared to the controls, that's the pink line, but these responses are not durable. With the adapter CAR, you can see that about 70% of the mice are long-term survivors, and this goes up above 85% with Lu011. So I will stop at that point. I would like to thank very many people for all of the data that I have mentioned. They're all listed on this slide. Unfortunately, it won't be possible to take questions, but thank you very much once again for the opportunity to present my data, and I hope to meet you all soon at a conference opportunity. Thank you very much.